Hi, welcome to this lecture entitled General Nmap Information. In this lecture, we're going to look at the different command line options for running Nmap and see how they can control what it does and how it outputs and things like that. So it's just kind of a general overview of running and using Nmap. So recall the stages of a scan. The first stage is host discovery, or the ping stage, where we find IPs that are online. The second was port scanning, which is where we scan for open ports on those IPs. The third is version detection, where we find versions of services running on those ports. The fourth is OS detection, where we guess at what operating system the computer is running. And the fifth is output, where we format and display the results to the user. So stage one is host discovery, and this is used to find active hosts to scan. Now there are three different types of host discovery that you can do. You can use ICMP, TCP, or UDP to check if hosts are active. And basically you send various types of packets to the hosts, and any reply indicates that a host is up. So we're just trying to get any reply out of it. If we can get something at the IP address to reply to us, then that means that there's a computer there, and we should follow up more later. So if we're going to do host discovery with ICMP, then we're just going to send some standard ICMP requests and see if the host replies. So the different options for ICMP host discovery. The first is -PE, which in the E is for echo. This would be an ICMP echo request, which is the same as a standard ping. If you use the ping command to ping an IP address, well, it sends ICMP echo requests and gets back an ICMP echo reply. So you can have Nmap just send standard echo requests. -PP sends an ICMP timestamp request, which is a different type of ICMP packet and probably one that you're not going to encounter in common usage. But it also necessitates a reply if the host receives it. And -PM is an ICMP address mask query, which again, not commonly used, not something you're going to see in practice, but the standard says that the host should reply. So by specifying these options on the command line, I can control which type of ICMP packet or packets that I want Nmap to use during host discovery. If the host sends any reply to any of these packets, then that just means that it's up. We're just trying to find out if the host is up. So unlike the port scanning phase, where we're trying to determine details of what ports are open or closed or anything like that, in this case, we're just looking for any reply to tell us that the host is up and running. So the next way you could do host discovery is with TCP packets. In this case, you send TCP packets to see if hosts reply. The command line options for this would be -PS, which would include a port list, and the S stands for SYN, because you're sending SYN packets. So you send a SYN packet to the listed ports. -PA, as you might be able to guess, the A would be for ACK. I'll send ACK packets to the listed ports. And if the host sends any reply, then that means that it's up. Now the third type of host discovery I could do would be UDP. In this case, I would send UDP packets to see, again, if the host replies. The command line option there, and there's just one, is -PU. U is for UDP. And I specify a port list, and I'll send a UDP packet to the specified ports. And again, I'm looking for any sort of reply. I might get a UDP reply, I might get an ICMP reply indicating that the UDP port is closed, but it really doesn't matter. Any reply means that the machine is up. And to look at the potential replies, you can always skim back at the UDP lecture, because the replies for UDP scanning and the replies for UDP host discovery are the same. So let's look at an example of controlling host discovery on the command line here. So if I run Nmap with these options, I'll have -PE, which is for the echo request, PS, which is for a SYN TCP packet, and I'm going to say, okay, I want you to send SYN packets to port 80 and 443. And then I would have -PU to say, I also want you to send a UDP packet to 5670. So during host discovery, Nmap will send these to each host in the range. So we get that echo packet, the SYN packets, and the UDP packets. And I just want to make sure that we're really clear that these packets are sent to every host in the range that I specify. And all I'm looking for is a reply to any of them to tell me if the host is up. This is not port scanning. I'm not specifying ports to see if the port is open or closed or anything like that. I'm just trying to get any packet back in the hopes of confirming that that IP address has an actual computer connected to it. So by default, if you don't specify any of these host discovery options, Nmap will still do host discovery, And by default, it will send an ICMP echo packet, an ICMP timestamp packet, a SYN packet to port 443, and an ACK packet to port 80. So it'll send those 4 packets to every host in the list and just look for any reply. So stage 2, after we're done with host discovery, is port scanning. Well, we've already discussed port scanning in a lot of detail, actually. In the previous 2 talks, I talked about TCP port scanning and UDP port scanning and gave you all sorts of details about how they work. So we don't need to do any details here. But just to briefly remember, the TCP scanning options would be SYN, ACK, null, fin, Christmas, etc. The UDP is just one basic UDP option. But one thing I didn't mention before is that you can specify the ports you want to scan for using this -p. It's a lowercase p, and then the ports you want option. If you don't specify which ports you want, then by default, Nmap will use the 1,000 most common ports. And those are the 1,000 most common as defined by the people who wrote Nmap. So they said, we think these are the 1,000 most commonly used ports, and they make those the default. But you can specify any set of ports you want. So as an example, if I use this Nmap command, well, this is doing a SYN scan, because I specified a SYN scan, of ports 22, 23, 24, and 25, which I specified here after the -p, port 80, and port 443. So after I've done my port scanning, I move into stage 3, which is version detection. In version detection, I'm going to go and I'm going to connect to the open ports that I found in stage 2, and I'm going to try to determine the version of the services that are running on those ports. Now the command line option for this is -sv. So as an example, if I use this command line option, well, this will perform a SYN scan, again, because I've specified the SYN scan. And then I also specify, after the SYN scan, perform a version detection scan. And I'm just going to run it on this one host. If you don't specify and specifically request version detection, then Nmap will skip this stage. So you have to specifically request it in order to get it to run. So stage 4, after version detection, would be operating system detection. And in operating system detection, basically, Nmap sends a lot of strange network packets to the host, analyzes the response, and uses that analysis to try and guess the operating system. It's really a fascinating approach that they take, but it's fairly inaccurate, but it does give you some good ideas of what might be there. In order to do it accurately, well, reasonably accurately, you need at least one open and one closed port. Now the command line option for this is -O. So as an example, if I specify this Nmap command, well, I'm going to perform a SYN scan because I told it I want to perform a SYN scan. And then I told it I want you to perform an operating system scan too, OS detection. How does this work? I mean, if you do operating system detection, what does that really do? I mean, how's it making this happen? So the observation that the Nmap authors made, and it's a good one, is that networking protocols are standardized, but multiple implementations of them exist. So even though there's a standard for IP and a standard for TCP, different implementations of them have been built. For example, Windows 7 has a different TCP implementation than Linux. Well, because Windows 7 was written by different people. A different team of programmers implemented its TCP stack than the programmers who did Linux. They were all basing their implementation on the same standard for TCP, but the actual code that they used to implement it and the strategies that they came up with were different. And so because of this, there are slight differences to the way various implementations respond to packets, and we can use those differences to help us distinguish between the implementations. So a specific example of this would be reset packets. The TCP standard says that a reset packet can have an error message attached, and the keyword there is can. It doesn't say it must, it just says it can. Well, some operating systems include an error message and others don't. So if a reset packet is being sent, it's usually because there was some sort of error included, error that caused the reset packet to be sent, like receiving a packet that you don't know what to do with, you send a reset packet back in TCP. And so some operating systems will include an error message to specify what the problem was, some won't. So I can use that to help me distinguish between operating systems. Other techniques that Nmap uses It analyzes the random sequence numbers from the TCP three-way handshake. So you may remember in the TCP lecture, I mentioned that when you initiate a connection in TCP, both sides end up generating a random sequence number. Well, what does that really mean to generate a random sequence number? The standard doesn't specify exactly how it has to be done. So different operating systems do it differently. Some of them will just use a continually increasing number, some of them use a truly random number, and the various choices that they make will impact what the sequence numbers are. So Nmap could initiate connections, get back a set of the randomly generated sequence numbers, and analyze that set to see if it can determine anything about the OS. Another technique is it could send some really strange ICMP packets and get the response, some really obscure or uncommonly used packets, and see what the reply is. And then another, and this one's probably my favorite, is that it sends a bunch of invalid packets. So they looked at the TCP standard and said, well, there's a whole bunch of potential types of packets that the standard doesn't say what to do. I mean, they're nonsense. They don't mean anything useful, but I could send invalid packets and see how different operating systems respond. And there's other techniques that they use as well. So basically, the Nmap authors have come up with a series of strange packets to send, and they send these packets to a bunch of operating systems that they know about, that they know what they are, see how they reply, and they build a database. And then when you want to do OS version detection, you send the same set of packets, you get the set of replies, and you compare to the database to see if you can figure out exactly what operating system it is. So the last stage of Nmap is output. And you can actually control the format that Nmap prints its output in. You should experiment with them to see what you think and see which one might be the most useful to you. So there's three options we're going to talk about. The first is -o_N. This would be the default output, human readable. The N is actually for normal output. This is what you've seen so far when we've done demos with Nmap and you've experimented with it. -o_X is XML output. And XML is good for importing into other programs because it's a very structured output that can be easily parsed because there's good libraries for it in a variety of programming languages. So if you had a separate program that was going to read in your scan output and process it in some way, XML could be a good format for you. And the last is -OG. G stands for greppable output. grep is a command line program on Unix that's used to kind of parse through strings. And so greppable output puts all of your useful information about a host on single lines, and it separates it strategically using good separator characters so that you can do string processing in order to quickly get the results. So ON is really more human readable. This is what you're going to see by default, and it's what you want to use if you want to read the output manually. If you have a program that's going to analyze the output, you'd either want to use the XML output or the greppable output. Your choice, depends on your preferences. So let's look at an example here. So I've specified, once again, the SYN_SCAN. If you haven't noticed, I really like the SYN_SCAN. And then I say, I also want to do a greppable output, and I want to put it into this file. You have to specify the output file when you use one of the options for the output. And so I specify _o_G outfile.txt. And this is going to perform that SYN_SCAN, and it's going to write greppable output into that file. So, summing up, Nmap has 5 stages, and you can use command line arguments to control each stage. We've only covered a very small subset of Nmap's options, so I encourage you to use the Nmap book to learn more. There's a lot of options and extendability in Nmap. It has an entire scripting engine, for example, so you can write separate programs to run based on what Nmap does, just to improve its results or to do specific types of port scanning queries. It's a very, very, very powerful tool. So, thanks.